Well, good afternoon. Thank you for joining our webinar series. We're very happy to welcome all of our attendees. I noticed that we have some world-renowned experts online. I'd like to give a special thanks for their participation. Today, we're talking about expert applications of our IEC methods for water, wastewater, lightning protection. Just a quick review of our webinar series that we've been conducting. This is the fifth of our series, focusing on the applications of the material that we've presented up to now. I'd like to introduce myself, Mark Hendricks, and my colleague, Stephen Weber.
Hello, everybody.
Thank you, Stephen. So today's session is really focusing on putting to use a lot of the material that we've already been discussing in our previous sessions. And it really is intended to bring together the application of these methods. And what's really nice about the IEC methods is it really walks you through a system from start to finish. And we'll see that in our session today by covering these topics, starting with risk. We talk about the design, the products, the installation, and we finish with a review of the quality control methods that we use and our turnover book methods. And what's really great is that the IEC methods actually give you really detailed instruction in how to walk through the quality control methods of a project. And that's what we'll see. So water, wastewater industry considerations. Well, we know that lightning and surges disturb all manner of processes, and we know that sewage plants play a key role in the water resource industry. And it's not just that you can damage your equipment, which is, of course, very valuable, and these are very important parts of our society, but it's also a threat to our environment. When you have uncontrolled damage, when you have uncontrolled discharge of water effluent, it can really pose significant health and safety threat to our environment. We see that all manner of equipment is subject to damage, power supplies, measuring systems, from direct strike and also from indirect strike. But there's also things like load switching and heavy duty motors going on and offline that can also introduce surges into a system. So even the day-to-day operations of a plant such as this can actually contribute to some of the damages that you can see at a plant. So risk and mitigation, that's what we like to talk about. But we're talking about the protection of a wastewater treatment plant when it's needed the most. So picture 2 o'clock in the morning on a Saturday, and you're experiencing a lightning storm and a heavy thunderstorm, downpours, right when a water, wastewater, sewage plant is under the most stress, you get lightning strikes. And so it's really a matter of protecting a system when it's really needed the most. Sewage plants are especially vulnerable because of the risks. They're large in size, they're spread out, you have a lot of equipment that's all part and parcel of the entire network of the plant. So a lightning protection system is designed to protect all of that equipment, from the external to the internal lightning protection and lightning equipotential bonding. And in our previous seminars, we talked about these aspects in great detail. And we showed that the external lightning protection protects the buildings from fire, mechanical damage. The internal lightning protection prevents hazardous sparking. But we also looked at equipotential bonding, and we took a close look at what surge protection serves as a way to control the voltages between your electrical systems and that metal bonded system. And of course, the goal is to optimize the availability of the installation. But if you're a plant operator, the goal is to keep the plant running when you need it the most. So we start with risk management. The IEC methods allow you to evaluate and to calculate your risk. And we do this through a system that looks a lot like an interview process. where we go into great detail about the structures of the buildings. We look at the actual thunderstorm days per year that you can expect. We look at the structure itself to evaluate what its collection area is. What is the likelihood that lightning will directly strike or strike nearby that structure? In this process, we take a really close look at the zones. What's actually inside of these structures? What are the zones and what's the damage that can be incurred into these critical areas? We take a really close look at the supply lines. What's coming in and out of these structures? You may have high power feeder lines. You could have electric signaling lines. You'll have, of course, the piping structures that are bringing the effluent into the plants. We take a look at the properties of the plant. What's it made of? What's the treatment on the soils? We take a look at the loss and then the cost of protection. And this all goes into the calculation to discover your risk. And that's what we show on this slide. You can calculate the risk to human life, to service to the public. Of course, this is a sewage plant, so we're really looking at economic value, but this can be tailored for your plant. And that's what's really great about the risk management process, is you discover what your risk if you do not have protection. And then you apply necessary and sufficient measures to control that risk. So here we show the risk before you've applied any measures. And then when you start to apply protection measures, like the class of lightning protection system, we can see that an LPL level 1 will be a little bit overboard. You can control the risk to well below a tolerable threshold. But we can also show that you can apply a lower lightning protection level, such as LPL 3, and control your risk without going overboard. Because we know that when you apply your measures, the higher level of LPL, such as LPL 1, will end up costing more. So we're trying to control the risk without incurring excessive spending to get the result that we need. So we've calculated the risk, we've calculated the LPL level that we need, and then we can apply that to all manners of the lightning protection system. So we're going to focus on the earthing system first. And at a water wastewater plant, you'll see something that very much looks like a type B ring electrodes at these plants. And I like to show this table because we can derive how much earthing that we need to apply for the site. How many earthing rods, what amount of conductor in contact with the soil. And so a chart that we see in the upper right corner shows us that the higher class of a very detailed class 1 system will have more conductor in contact with the soil. And we've talked about that in the past, and it's really a matter of deriving your risk and then applying correct measures. So what's nice about this slide is it gives you a preview of what that ring conductor will look like. And we show some of the methods that are applied. You can do the fall of potential testing to derive your earth resistance, and then you can apply those measures to discover what your actual ring conductor needs to look like. So a water plant like this will look like an intermeshed earth termination system. And that's what's nice about the diagram below. You can see that it's composed of a series of ring electrodes around the structures that are all interconnected. And this is another contributing factor of why it's so important to apply these measures. The electrical bonding and your soil conductors, it's all critical, because if you get struck on one end of the plant directly, that electrical lightning charge can really travel through and cause a lot of damage throughout the system. So what's nice about a slide like this is it shows us that it's really consistent of a intermeshed electrical system. So you're on your site and you're inspecting that earthing system. And what's really nice about a slide here is that we can use a Clampon meter that is an active source. It actually has a send and receive type function. Think of it like sonar for your earthing, where you can ping into the pigtail and it will tell you that it's hearing that ping return, and it calculates the impedance. So what we see when we apply this inspection method is that you can discover that you have very low impedance loops where it's looking above ground and below ground, and the meter shows you that you're in a loop, but it shows you in this case that you've got very good control, 0.062, 0.029 ohms at these adjacent conductors. And now in the corner, we see a 19.0 ohm reading. And this reveals that there's a problem with that earthing system. So this is a really nice example of being able to show troubleshooting of your earthing system while it's being developed, while you're doing your installation, so that you can take measures and repair things before it's too late. And that's what's important about this type of site inspection and ground grid troubleshooting. So we've established the earthing, and now we want to take a look at the actual air termination and down conductor system. And these are a couple of really nice models that show the placement of the air terminals to create a rolling sphere design that will offer suitable protection over the water control system, the water process buildings. And in the photograph to the right, we can see the lightning air terminals around this structure, the finished result with the down conductors meeting into the soil. Here are a couple of other nice illustrations showing a similar system around the water tanks with the control buildings. In the lower right, we see the system overlaid onto a Google Earth image that can help represent to the customer that we provided suitable and necessary and sufficient measures to offer a rolling sphere protection around the structure. And this is essentially the basis of the external lightning protection system. But recall that each of these air terminals are driving down conductors, so you have currents entering the soil around this structure. And we talked about the earth termination system, and here we're showing the external air terminals, and this is part of that external system to avoid direct damage from lightning strikes onto these structures. And here's a view of a system that we helped work on in Florida. And in this case, the system was brought online and right away suffered lightning damage. Florida, of course, has lots of lightning storms. And when we reviewed the system, we discovered all the critical issues with inadequate earthing, incomplete bonding, and inadequate surge protection. So this is a great example of having a very complex system put in place, but some of the key pillars of lightning protection were missed and resulted in extensive damage to the system. And it turned out that the damage far exceeded the cost of doing it right the first time. So we take a look at what a water treatment electronic block diagram might look like. And of course, it's a very complex system. You have a wide variety of flow chemical measurement systems, high power pumps to move the material through the facilities and through the process. This is, in the top image, is a nice illustration of what's called a lift station, where it uses gravity from the homes in the community to collect the waste materials, and then it lifts them through pump action to bring all that material back to the central processing facilities. And below you see just a typical block diagram of how complex the electrical apparatus with the control systems, power over Ethernet, CAN bus, and even the pump systems themselves. We also see very complex control room systems with all manner of computer process monitoring, security systems, measurement, and motor control systems. And this is just a typical example of what a wastewater facility might look like. And the intent is to illustrate what's going on behind the scenes. So as we start talking about the actual surge protection methods, I wanted to take a moment to illustrate what the SPD, the surge protection device, is actually doing. You have an unprotected side where the circuit has exposed wiring, and you have a protected side coming into your marshalling cabinet where all of your control systems will be. And in this illustration, we can see a spark gap device, which is very robust, handling the incoming surge energy. It's controlling the voltage across the wires relative to earth. And then we see what is essentially a series element that offers a fusing type process. So in one device, we have the surge protection and fusing for surge current control. And then on the protected side, we're showing what looks like a high powered Zener voltage control device to offer the best protection at the protected side of this type of equipment. And we use this type of a SPD device throughout the next several slides where we're discussing applications in detail. Bulletproof protection on both ends. It's important to protect the control cabinet, but it's also important to protect the equipment out in the field. You'll have flow transmitters and such. And what's important is to protect on both ends. And that's what we see in an illustration, a photograph like this, where we have the wiring systems coming into a marshalling cabinet, and we want to demonstrate that the surge protection devices need to be applied on both ends of that cable system. Critical pump and CAN bus protection. What's really important, and we'll see this in more of our slides, is that we apply surge protection at the actual pumps, at the point of use. But in this case, these pumps are often, very often, outdoors, and they're actually adjacent to what is the down conductor system, the actual lightning protection system. So we have a very high likelihood that you're going to have ground potential rise right at these pumps. So what's important is to provide both type 1 control of that lightning induced ground current and type 2 surge protection to divert the remaining transient away from the motor systems. And here in this illustration, this photograph, we see the data protection for that pump system at these point of use applications. And that's why it's important to apply the SPDs on both ends of that CAN bus data control system. So here are some diagrams of where you'll see these applications, so very common in a wastewater control system. You have very sensitive measuring equipment that's monitoring the flow of fluids, monitoring chemistry, and you'll have a pump and other AC powered devices. And what's really important is that we're tracking the shield of that cable. We're looking at the earthing of all of the systems, and we're monitoring the flow of water and wastewater with very delicate electrical control systems. In this slide, we're seeing an extended view of very typical system, and the illustration really is helpful because it shows us all of the aspects that we've already been talking about. Your equipment is bonded, your remote metal, I like to use that term, floating metal, those elements are all bonded, and that controls the voltage across the metal components. And then you apply your surge protection to control the voltage across the electrical circuits. So what's nice about these diagrams, in one diagram, you have the opportunity to see many of the aspects of lightning protection that we've been discussing throughout our webinar series. Here we see a very similar application with the pH control systems. You're monitoring delicate chemical balances so that the organic processes of the water wastewater facility are properly maintained. And we can see that you have a combination of 4 to 20 milliamp type circuits in addition to AC power control systems as well. So again, this one diagram shows you all of the aspects that you need to pay attention to control all the pillars. And remember, we've talked about things like avoiding or missing one of the aspects is likely to induce damage. Here's a nice illustration of a Profibus type circuit where you have a loop control system throughout the plant, and any of these nodes that are left unprotected will have the opportunity to introduce surge energy into that bus, and you will damage not only the sensors that are locally applied, you'll have the opportunity to damage the entire Profibus network, going all the way back to the control panels at the marshalling cabinet in the control rooms. This is a more detailed illustration of a Profibus system. And what's really important is that there may not be an external power supply. So you're really counting on controlling the voltage control system that's coming into that transmitter, but you're also having to control and protect the power supply that's back at the control system. So this actually may be a combination of hazardous zones as well, because you may have effluent gases that will cause additional sources of damage. If you have a ignition source anywhere near these gases, you have a very serious concern about explosive environments. So switchgear and motor pumps, this you'll find all over a wastewater plant. You'll have surge protection devices applied at the control systems as well as on the AC power system, both in front or behind the variable speed drives. The SPDs have to be arranged in a very clear and concise manner, and you always have to pay attention to your bonding. So very similar illustration. You have in one illustration the requirements to show the cabinet grounding, the loose metal, for instance, the door of the cabinet needs to be bonded as well. And then you have to have your earth bonds for the surge protection devices throughout the electrical control system. So as I like to say, in one diagram, you have all of the aspects of bonding and surge protection illustrated. So here we see a nice photograph showing some of the aspects we've been discussing. You have a flow meter, so you'll have a data line, you'll have a protection device installed directly at the flow meter at the point of use, and that's going to be married with another surge protection device at the marshalling cabinet. But also here you see the opportunity to put surge protection on the AC power lines as well. And you can take a close look at this cabinet. You can see you have your bonding wires for the earthing of the surge protection device. You'll have earthing within the cabinet. And like I say, in one photograph, you can see many of the aspects that you have to pay attention to. Here's a nice photograph of the marshalling cabinet inside of the control room. And it also demonstrates the aspects that we've been illustrating. You have bonding jumpers on the door so that the door does not float relative to the control systems. You have bonding on the surge protection device. You have bonding in the master ground bar inside that cabinet. But what's important is that this is the other end of that flow meter. So we're installing surge protection directly where the wiring enters the control cabinet to provide the best control of that voltage before it hits the IO control systems. Power over Ethernet is going to be seen widely throughout a wastewater treatment plant as this. You'll have security cameras, you'll have power over Ethernet apparatus at security gates, and what's really important is that you have a suitable power over Ethernet protector applied on both ends of that security system. And here you can see it's applied directly at the cabinet before it enters the switch and the network computer systems. And as I like to say, it's at the point of use, as close as possible to the sensitive controllers and routers. Here we see a very complex CAN bus control system, and what's important about a photograph like this is that you can see your surge protection devices are installed as the wires enter the cabinet at a marshalling point before the wiring systems get into the CAN bus nodes. And in one photograph, we have an opportunity to see all the earthing and bonding. We have a central node for bonding down in the lower center of the cabinet, and this provides that single point ground, and this earthing would be connected to your earth electrode system. And what's important is that you have that control of your surge directly at the point of use. In one photograph here, we're showing surge protection devices at all the pump controllers, so that each of these critical pumps throughout a structure, like in this case, it's the water bubbling system, where it allows the sediment to easily filter down to the bottom of the tanks. And in this photograph, you can see scattered throughout this system many pumps. Each of these pumps will have an SPD device installed correctly at the point of use. What's really important is to have comprehensive site protection with a combination of type 1 and type 2 SPDs on these exposed panels. As I mentioned, you'll have these pumps that are in fact outside, and they're directly associated with the down conductor systems. And if you have ground potential rise, you'll have large lightning currents being induced into these pumps. And that is why we pay a lot of attention to make sure it has both type 1 and type 2 protection on these panel systems. And one of my customers, I believe he said it the best: we only have to wait for the next lightning storm to find the controllers and pumps that have not been properly protected. And this is exactly the case, where when lightning comes, you will see where the weakness in your systems are. And that is exactly the problem that he suffered. And by allowing the lightning to have to damage his system, he was very concerned about controlling it for future storms and prevent future damage. So here we have a few photographs showing the SPD applications at the motor control panels inside of the water process facility, where the SPD is directly on the main switchboards to provide protection for the loads on those switchboards. And here's the surge protection devices installed downstream from the main MCC directly at the pumps. And municipal customers know that when there's a problem, it will always flow downhill. Well, we've heard versions of that story, but in the wastewater industry, that is all too true. And the last thing that an operator at a waste facility needs is a phone call from the mayor whose lift station has gone offline. And then we really know when it will flow downhill. So the lift station control systems will have their own sets of challenges. You'll have AC power protection, but you'll also have transmitters, point to multi-point radio networks that are communicating the status of the remote lift station back to the main control centers. And here we'll see examples of having an RF surge protection device installed directly on that coaxial cable as it enters the cabinet. bonded directly into the electrical bond system in the cabinet. And you have a nice illustration showing flow meter wiring coming up into that control cabinet. So here we have, at these remote lift stations, many opportunities where damage will disrupt this lift station, which will affect the entire network into the main wastewater control centers. So we've conducted a detailed project to install lightning protection systems. And one of the things that's very important is to show that your system meets the design intent. The IEC methods give us a really great method. It actually gives instruction on when to put in inspections and when to monitor your project from start to finish. And so in one matrix like this, you can evaluate all of the lightning protection methods that were installed. You can see when they were mobilized, when they were inspected on the site, when they were inspected by final certification. You can look at your final review of the air terminals themselves, and you also look at the ground bond measurements. And this is all part of creating an end-to-end quality system that delivers the planned design in a very coherent and concrete report. And that is part of what we can turn over to the customer as a final inspection with a complete set of punch list walk-down notes, the rolling sphere coverage for the site. We show that compliance matrix, and we show the SPDs were properly installed on the site. And that gives you full IEC Part 3 and Part 4 compliance. And these are just some of the methods that we employ to properly protect a water wastewater facility. So I'd like to give an opportunity for questions today. I know we covered a lot of material. I believe we've covered the aspects of our presentation. Stephen, if we have any questions, I'd like to give an opportunity to see that.
Yes, Mark, we did receive a few questions. One of the questions regarding earth electrodes and ring earthing, can you provide the same level of protection with individual earthing electrodes rather than a ring earth electrode?
When I hear the word individual electrodes, is that implying like a type A system?
Yes, I think the question. Yes, I think the question refers to does a type A lightning grounding system provides the same level of protection than a type B grounding system? In other words, does individual earth rods provide the same level of protection than a ring earth conductor?
Well, I think that the concern about a type A system on a large interconnected plant like a water waste plant is that if you have type A electrodes scattered throughout the plant, each of those will be adequately protected, but you'll have interconnected lines between them. And now you have an earth electrode that isn't connected to the other part of the plant. And you'll have an opportunity to have voltage built up from end to end. And so if you think about it like water in a pipe, in a cookie sheet, you've now introduced the opportunity to have a very high potential on one end, and the lightning currents will want to flow, and probably through the electrical and electronic control systems.
Yes. I also just want to add that if you install an individual earth rods for a lightning protection system, you need to make sure that you install the adequate number of individual earth rods for that lightning protection system, and also that they are the adequate length in contact with the soil that is in line with the class of lightning protection system that you are implementing and the soil resistivity of the site. I believe if you do those things, you have the correct number of electrodes and they are the adequate length that they need to be, I believe that using earth rods would also provide sufficient protection than using a ring. Mark, did
Sure.
you mean it's necessary to install both a class 1 and a class 2 at the point to protect equipment? For example, for motors, just next to ground level, isn't a class 1 only sufficient?
Yeah, there's a lot to say that a class 1 would still be sufficient at that motor. In many of our applications, the customers are concerned about their motor systems. They've had experience with insufficient SPD applications, and so that was one of the reasons our customers were particularly concerned about installing both Type 1 and Type 2 at their motor systems.
Is there a maintenance aspect of SPDs that needs to be considered?
Well, that's why the monitoring of the surge protection device is important. In a high lightning environment, an SPD is stressed far more often. So both the selection of the SPD type and suitable maintenance programs to monitor the SPD health are important. The real problem is that you really don't know if a typical AC power SPD is nearing its quote unquote end of life. If you're in a high lightning area, it's reasonable to assume that every year you should be inspecting your SPDs. If you have direct strikes on your structure, it's quite reasonable to assume that you need to inspect and evaluate your SPDs.
Then a question about the distance between cabinets. If you have two adjacent cabinets, one feeding the other, do you need to install surge protection devices in both cabinets? What is that? How far can, that question about how far does the line need to be to consider SPD installation in both cabinets?
That's actually a really good question. And in the past, I've worked with other customers in the telecommunications and in the first responder industry. And there's sort of a rule of thumb that when you're more than something that might look like, meters, 30 meters apart, you have the opportunity to build up voltage from one end to the other. So for instance, it's possible to look at your wire gauge, your wire connections, calculate the impedance of that wire, and then run a simple rough order of magnitude. How many surge amps do you expect? What's the voltage across that wire? And in many cases, on the back of a napkin, you can establish that you have well over the insulation breakdown of the wire at the other end. So it's somewhat of a rough order of magnitude because you have to make an assumption about how much surge current is actually flowing through the wire. But it is possible to make some calculations based on that. And it goes back to using point of use surge protection.
Then can the clamping meter that you showed be also be used to measure lightning conductor loops? What is the maximum loop impedance that is acceptable?
So I believe that is the question is, can you evaluate your lightning conductor? Yes, you can evaluate the loop that the lightning conductor sees both above ground and below ground. And that particular type of meter is, as I mentioned, it has two sets of Hall coils in it. And it's, as I mentioned, it pings the circuit and then listens. So you can evaluate your above grade lightning down conductor system and then the below grade to basically show that you have an interconnected loop above and both below grade. As for the ideal reading, that's somewhat, I'll say that's somewhat of a customer requirement. For instance, we have customers that mandate that they want less than 1 ohm earthing system. So it's possible to use that type of meter to evaluate each node. What's more important about that question is that the readings are consistent around a building where you have typical readings and you don't have large variations. As we illustrated in one of our slides, we had very low impedance measurements, which you would expect from very good contact and very good conductors, and then another reading that's order of magnitude higher. That points to that conductor having a problem.
I just want to add that if you have knowledge, technical knowledge on the proper measuring techniques, you can actually use this clamp meter to measure loops and multiple bonds, ground bonds, as long as you have that knowledge of how the loop is supposed to be, completed. What exactly you're measuring. You can actually measure multiple bonds, and that's one of the questions that was asked here, is how many bonds can be measured by this loop. So that's why I'm answering that question as well. You can measure multiple bonds as long as you have in-depth knowledge of how the loop is supposed to be. And sometimes when we're on site, we even make use of jumper wires to route the loop in certain directions that we want it to flow in order to measure the adequate amount of bonds that we have to measure. Yes, Mark, that is all the questions that that was submitted during the webinar.
Great.
I just want to let everybody know that you please feel free to submit more questions directly to my email. We will be submitting this webinar recording to everybody, and you will be able to find it on our DEHN website and our DEHN YouTube channel.
Excellent. Thank you, everybody, for your attendance today.
We have one more question that just came
great.
in. John asked, I got confused about where is the best location for the control and data SPD? Close to the equipment to be protected, or to the entry of the cabinet?
Well, for best practices, it's both ends. You put the SPD at the point of use of the flow meter, for instance, and then at the marshalling cabinet entrance, so that it's as close as possible to the where the energy is entering the cabinet.
Yes, I agree.
I believe that answered that question. Okay.
Yes. Thank you, Mark. Thank you, everybody, for joining us.
Great. We look forward to having participation in our upcoming webinar series, which will be announced through our blog and through our website, and continuing email on the participation. Thanks again, and have a great, safe day.